According to the 2020 National Electrical Code, Section 517.13, grounding paths for alternating current systems require that equipment grounding conductors comply with Section 250.118. Section 250.118 addresses equipment grounding conductor continuity, stipulating that the equipment grounding conductor shall be continuous throughout its entire length. When an existing distribution system relies solely on the conduit as the grounding means, it falls short of meeting the requirements outlined in the National Electrical Code. As part of a renovation project involving patient care and sleeping areas, the addition of ground conductors to branch circuits and panel feeders is crucial for establishing a continuous grounding path. Therefore, it becomes necessary to supplement the existing system by introducing a ground conductor alongside the existing panel feeders. This action is essential to ensure the proper grounding of the entire patient care area and patient sleeping area, aligning the electrical system with the National Electrical Code regulations. The absence of a dedicated equipment grounding conductor, relying only on the conduit, creates a potential safety hazard and violates the prescriptive requirements. A dedicated equipment grounding conductor offers a lower impedance path for fault current, facilitating faster operation of overcurrent protective devices such as circuit breakers or fuses. This rapid clearing of ground faults minimizes the risk of electrical shock to patients, staff, and visitors. The National Electrical Code emphasizes the importance of a robust and reliable grounding system in healthcare facilities due to the heightened sensitivity of patients and the increased use of electrical medical equipment. Proper grounding minimizes leakage current and electromagnetic interference, which can disrupt the function of sensitive medical devices and compromise patient safety. When retrofitting or renovating electrical systems in healthcare facilities, it's important to perform a thorough assessment of the existing grounding infrastructure. This assessment should identify any deficiencies or non-compliance issues and determine the appropriate corrective actions to bring the system up to current standards. In addition to adding a ground conductor to the panel feeders, it may also be necessary to upgrade the grounding electrode system, such as the grounding rods or plates, to ensure adequate grounding capacity. The size of the equipment grounding conductor must be carefully selected based on the size of the ungrounded conductors in the circuit. National Electrical Code Table 250.122 provides guidance on the minimum size of equipment grounding conductors for various circuit ampacities. All grounding connections must be made securely and reliably using approved connectors and methods. Improper grounding connections can create higher resistance points in the grounding path, which can impede the flow of fault current and compromise the effectiveness of the grounding system. It's important to avoid the use of devices that depend on screw shell contact for the grounding path. These devices, such as receptacles with screw shell connections, are not considered to provide a reliable grounding connection and are prohibited in patient care areas. Instead, use receptacles that have a dedicated grounding terminal that is connected to the equipment grounding conductor. All metal enclosures and equipment within the patient care area must be bonded together to create an equipotential plane. This equipotential plane minimizes voltage differences between conductive surfaces, reducing the risk of electrical shock. Bonding can be achieved by connecting all metal surfaces together with bonding jumpers or by using metal conduit and fittings that are listed for grounding purposes. The National Electrical Code provides detailed requirements for bonding in healthcare facilities in Section 517.13. During the installation of new branch circuits and panel feeders, care must be taken to avoid creating ground loops. A ground loop occurs when there are multiple grounding paths for the same piece of equipment, which can create circulating currents in the grounding system. These circulating currents can cause nuisance tripping of circuit breakers and can also increase the risk of electrical shock. To avoid ground loops, it's important to ensure that there is only one grounding path for each piece of equipment. This can be achieved by using isolated grounding receptacles or by using a single-point grounding system. All electrical work in healthcare facilities must be performed by qualified and experienced electricians who are familiar with the specific requirements of the National Electrical Code for healthcare facilities. The electrical system must be inspected and tested by a qualified electrical inspector to ensure that it meets all applicable codes and standards. Regular maintenance and testing of the grounding system is essential to ensure its continued effectiveness. Grounding connections should be inspected periodically to ensure that they are secure and free from corrosion. The grounding electrode system should be tested to verify that it provides adequate grounding capacity. The results of these tests should be documented and kept on file. In summary, when renovating patient care areas in a hospital, it's important to upgrade the grounding system to comply with the requirements of the National Electrical Code. This includes adding a ground conductor to the existing panel feeders, upgrading the grounding electrode system if necessary, and ensuring that all grounding connections are made securely and reliably. By taking these steps, it is possible to create a safe and reliable electrical system that protects patients, staff, and visitors from the hazards of electricity. Remember to always consult with a qualified electrical engineer or contractor to ensure that the electrical system meets all applicable codes and standards. It is always important to verify the specific requirements of the authority having jurisdiction, which may have additional or more stringent requirements than the National Electrical Code. Firstly, ensure that all components used in the grounding system are listed and labeled for their intended use. Secondly, use appropriate tools and equipment for making grounding connections. Thirdly, follow the manufacturer's instructions for installing grounding connectors and hardware. Fourthly, provide adequate mechanical protection for grounding conductors to prevent damage. Fifthly, document all grounding system modifications and upgrades. Sixthly, train all personnel who work on the electrical system on proper grounding practices. Seventhly, establish a regular maintenance schedule for inspecting and testing the grounding system. Eighthly, keep accurate records of all grounding system inspections and tests. Ninthly, promptly address any grounding system deficiencies or non-compliance issues. Tenthly, continuously improve the grounding system based on experience and feedback. The information provided here is intended as a general guide and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or contractor for specific recommendations regarding electrical system design and installation. In addition to the equipment grounding conductor, the National Electrical Code also requires a supplementary equipotential bonding system in patient care areas. This equipotential bonding system is intended to minimize voltage differences between conductive surfaces that may be accessible to patients. The equipotential bonding system consists of a network of bonding jumpers that connect all metal surfaces together, such as receptacles, light fixtures, medical equipment, and plumbing fixtures. The bonding jumpers must be sized according to National Electrical Code Table 250.122 and must be installed in a manner that provides a low impedance path for fault current. The equipotential bonding system is particularly important in critical care areas, such as operating rooms and intensive care units, where patients are more susceptible to electrical shock. In these areas, the National Electrical Code requires that all exposed conductive surfaces within the patient vicinity be bonded together to create an equipotential plane. The patient vicinity is defined as the space within 6 feet horizontally and 7.5 feet vertically of the patient. The National Electrical Code also includes specific requirements for isolated power systems in operating rooms and other critical care areas. Isolated power systems are designed to prevent electrical shock by isolating the patient from ground. These systems use a special transformer that isolates the electrical circuit from the building's grounding system. In the event of a ground fault, the isolated power system will not trip a circuit breaker, but it will activate an alarm to alert medical personnel to the fault. Isolated power systems are typically used in conjunction with equipotential bonding systems to provide a high level of electrical safety in critical care areas. The installation of electrical systems in healthcare facilities is a complex and challenging task that requires careful planning, design, and execution. It's important to work with experienced professionals who are familiar with the specific requirements of the National Electrical Code and other applicable codes and standards. By following these guidelines, it is possible to create a safe and reliable electrical system that protects patients, staff, and visitors from the hazards of electricity. The size of the equipment grounding conductor is crucial. Using too small of a conductor could lead to a hazardous voltage potential in the event of a ground fault. National Electrical Code Table 250.122 dictates the minimum size based on the overcurrent protective device protecting the circuit. For example, a circuit protected by a 20-amp breaker requires at least a 12 American wire gauge copper equipment grounding conductor. A 30-amp breaker requires at least a 10 American wire gauge copper equipment grounding conductor, and so on. It is permissible to upsize the equipment grounding conductor if desired, but never reduce it below the minimum size specified in the table. The type of equipment grounding conductor is also important. Common types include copper wire, aluminum wire, and rigid metal conduit. Copper is generally preferred for its low resistance and corrosion resistance. Aluminum can be used, but it must be sized larger than copper to achieve the same level of conductivity. Rigid metal conduit can also serve as an equipment grounding conductor if it is properly installed and meets the requirements of the National Electrical Code. However, using only conduit as the grounding means is not permitted in patient care areas. A supplemental equipment grounding conductor must also be run with the circuit conductors. When installing equipment grounding conductors, it's important to avoid sharp bends or kinks, which can increase the impedance of the grounding path. The conductor should be run as directly as possible between the equipment and the grounding point. All connections must be made with approved connectors and fittings that are listed for grounding purposes. The connectors must be properly tightened to ensure a secure and reliable connection. It's also important to protect the equipment grounding conductor from physical damage. The conductor should be routed in a manner that minimizes the risk of being cut, crushed, or otherwise damaged. If the conductor is exposed to physical damage, it should be protected by conduit or other means. Regular inspection and testing of the grounding system is essential to ensure its continued effectiveness. The grounding connection should be visually inspected for corrosion, looseness, or damage. The resistance of the grounding path should be measured to verify that it is within acceptable limits. Any deficiencies or problems should be promptly corrected. The National Electrical Code requires that healthcare facilities have a comprehensive electrical safety program that includes regular inspection and testing of the grounding system. This program should be developed and implemented by qualified personnel who are familiar with the specific requirements of the National Electrical Code for healthcare facilities. Remember to always prioritize safety when working with electrical systems. If you are not qualified to perform electrical work, consult with a licensed electrician. Failure to follow proper grounding practices can result in serious electrical shock or electrocution. Grounding is a critical aspect of electrical safety in healthcare facilities, and it is essential to ensure that the grounding system is properly designed, installed, and maintained. In addition to the requirements of the National Electrical Code, healthcare facilities may also be subject to other regulations and standards related to electrical safety. For example, the Joint Commission, which accredits healthcare organizations, has specific requirements for electrical safety in accredited facilities. Healthcare facilities should also consult with their insurance carriers to ensure that they are meeting all applicable requirements for electrical safety. Firstly, perform a thorough assessment of the existing electrical system to identify any grounding deficiencies. Secondly, develop a detailed plan for upgrading the grounding system to meet the requirements of the National Electrical Code. Thirdly, use only listed and labeled equipment and materials for the grounding system. Fourthly, install the grounding system in accordance with the manufacturer's instructions and the National Electrical Code. Fifthly, test the grounding system after installation to verify that it meets the requirements of the National Electrical Code. Sixthly, document all grounding system modifications and upgrades. Seventhly, train all personnel who work on the electrical system on proper grounding practices. Eighthly, establish a regular maintenance schedule for inspecting and testing the grounding system. Ninthly, keep accurate records of all grounding system inspections and tests. Tenthly, promptly address any grounding system deficiencies or non-compliance issues.